I feel like I need the bell that says shame. All right. All right. It's okay. Okay, well, today we'll continue talking about optimization. I think we left off, we did golden section search, and well, I don't know, maybe I'll just wrap up golden section search, and then we will extend our optimization talks to I can't remember now. Multi-dimensional optimization. Just lost my train of thought. Okay, so the idea with golden section search, I think I added a link on CCLE also, which is a very, I think, a good video. So you pick kind of your left and right bounds. You're going to pick two middle points, which is around here and here, something like that. And if I call this A and I call this B, then this is, 0.618 of the way to R. And this one is, golden ratio 0.618 of the way to L, okay? And of course, the actual value is, there's a few more decimals than 0.618, but this is a good approximation. And the idea is you evaluate f of A and f of B. And then I think on Wednesday's class I said so this time we'll go with the, well, in our picture, A is definitely lower than B, but okay. So in our picture we'll say f of A is less than f of B. So then that means L and A and B form a triplet of points where we know a local min must exist between L and B. Okay, because also it's implied also that f of A is less than f of L. Okay, so we know that a local min must exist between L and B. Likewise, on the other hand, if we have the opposite, where f of B is less than f of A, then A, B, and R will form a triplet and we know a local min must exist between A and R. Okay, so we have that, and so once we calculate kind of f of A and f of B, we can eliminate about 38% of the interval, and we can shrink our interval by about 38%. And if we redo this, so in this case, according to our picture, f of A is less than f of B, so we have something like this now. So this was L, and this is A, and this is B. So L is going to remain L. B is going to become our new right bound. A is going to become our new B, because if I just say if this was 0 and this was 0.382 and this was 0.618, what we find is that L to here is 0.618 of the way to R. Okay, and so this means I can just reuse one of the values and I don't have to recalculate both midpoints again. Okay. We can reuse one of the midpoints and we just have to find the new A. Right? And so now I've got a new L, an A, a B, and an R. Okay. On the other hand, if our function was just the opposite, so if this was if the function looked like this, L, A, and L, A, B, and R, then we would just keep A becomes the new L, B becomes the new A. We would have to figure out a new B, and R remains R. So this is where f of A was less than f of B. Oh, I drew this picture wrong, but over here would be f of B is less than f of A. Something. I don't know. Okay, and we would pick here and here. Okay. And then so we, with each iteration, the gap between L and R shrinks by about 38%, and we continue to iterate until the gap between L and R is below our tolerance level. Is this okay? Any questions on golden section search? All right, so that's where the golden ratio comes in nice and handy. Okay, let's talk multidimensional optimization. All right, and here we're just going to look at we'll just look at one algorithm called coordinate descent. Okay, so one there's lots of optimization methods. You can just go to Wikipedia and type in mathematical optimization, and there's going to be a ton of things. We'll just look at coordinate descent because what coordinate descent does is it breaks down a multi-dimensional optimization problem into a series of unidimensional optimization problems. So we've covered a couple unidimensional optimization methods, right? We have the extensions of root finding applied to the derivative, and then we have golden section search. And so we can apply unidimensional optimization to this. If you were to take, if you take 102B, I'm pretty sure most 102B classes cover this, but I know mine, we cover gradient descent. Okay, so that's another multi-dimensional optimization method, and I cover that in 102B. Here we look at coordinate descent, and what this basically does is it breaks down multi-dimensional problem to a series of unidimensional problems. Okay, so how does this work? Well, let's basically you've got some function, let's say function of A, B, C, and D, and so this is a four-dimensional function. And we can imagine reducing this to just two dimensions, or having 20 dimensions. And basically, each iteration will have k subset steps. Okay, k being the dimensions of the function. So in this case, we will have 4 substeps. Okay, so you start with some initial values for A, B, C, and D. Okay, start with, we'll say A0, B0, C0, and D0. Okay, so you just start with some initial values for A, B, C, and D, and then what we do is we substep 1 is rewrite our function A, B, C, and D, where B, C, and D are set as constants. Okay, using kind of your initial values. So you set everything else a constant, and you allow only the first variable to be the only thing that varies. Okay, so this just becomes a function of just A now, right? If B, C, and D are set to be constants, then the function is no longer a function of 4 variables, but it's a function of only 1 variable, because everything else has been set to a constant. Okay, so now you have a unidimensional function. Unidimensional function of A, and then so you minimize f with respect to A. So you just find the minimum value, okay, and that we will set to be the next value, A1. Okay. Now that you have that, and the second step, now rewrite f of A, B, C, D. Okay, set A equal to A1, and C will be C0, and D will be set to D0, and so this becomes a function of B. Okay, unidimensional function, optimize it with respect to B, so, or minimize okay? And then that will become B1. And then you continue and you do this for each variable, okay? You set everything else to be fixed values, and it becomes, you reduce your multi-dimensional function to a single dimension, to a one-dimensional function, and then you optimize with respect to that one variable. So, so what this, I'll try to draw a picture. This picture might be a disaster, but I'll try it. Okay. So let's say we have a two-dimensional function. Okay. So we have a two-dimensional function. So it's a function, and so if we draw, let's say we've got some paraboloid, right? So this is supposed to look like some kind of bowl here. And basically, let's, we'll call this A, and we'll call this variable, this one over here will be dimension B. Okay. Okay, and so if I set, we will set B equal to B0. Basically, I'm going to just, I'm going to cut a slice I'm cutting a plane here where B is set to some value, okay? And so when it slices through our paraboloid, this is what we get, okay? We get a single-dimensional function, right? So you've got the bowl, but now you're slicing it, okay? So then when we look at that, this is what we see, okay? And we're going to minimize this, all right? So we say, so this is this is now a function of A, right? This is f of A, and we find this location here, minimize, and this will be A1, okay? So we find this spot right here, okay? And then so at the next substep, still have this thing. Okay, and then so now that I've found that, I'm going to take this and we will try cutting a slice like this now. Okay, and then when I do this, maybe the picture looks like that. I've cut a slice through the bowl in this direction. So with, this is at A equal to A0, or A1. Okay, so this becomes, this is now a function of B, and we've got a parabola, and we will minimize it right here. And that will be B1, okay? And we just continue slicing in one direction by setting it in a constant, and then once we've minimized it there, we draw a slice at that location. And we just keep going back and forth, and eventually this will lead us to the global minimum, okay? After each iteration. All right, does this picture kind of make sense? And it looks better in my brain, but this is what we have to deal with here. Okay. Okay. All right. So let's try an application of optimization, multi-dimensional optimization. All right. So let's do ordinary least squares regression, right? OLS. And let's just have one predictor, right? So we've got y hat equal to a plus bx. I know we usually write beta 0 and beta 1, but we'll just do this. Okay, and so let's say my data, we'll keep it real easy. My x goes 1, 2, 3, 4, and my y goes 2, 6, 4, 8. Okay, so when I graph this, it looks like this. All right. So this will be 1, 2, 3, and 4, and 2, 6. Okay, and then so we want to find what values of A and B will minimize the sum of squares residuals, which will be, we will say is the sum of y minus y hat squared. Okay. So keep in mind, y hat is the quantity a plus bx, right? That's what we have. Okay, so what we have now is we have a function. This is a function of a and b. What we're going to say the sum of squares residual is a function of a and b, because we want to find the slope and the intercept that minimize this sum of squares residuals. Now, I know least squares, it's already been solved. We know the answer, but just bear with me and say this is an interesting thing that we're going to do. Okay, so let's rewrite this whole thing. So we've got sum of squares residuals as a function of a and b, and so we will go through each data point. So the first one is going to be 1 minus, and it's going to be a plus bx. So that's going to be, I'm sorry, not 2. Y is 2. Y is 2 and x is 1. So our first data point, y is 2, x is 1. So I got 2 minus a plus b squared. Okay, and then the next data point, y is 6, and then we've got a plus, and then b is 2. So I've got 2b squared plus, and we'll come, and the next one is going to be 4 minus a plus 3b squared, and then lastly I've got 8 minus a plus 4b squared. Okay. All right, so this is my function written. We're trying to minimize the sum of squares residuals for a data set, right? So, yes? Is that known as sum of squares error, SSE, I think SSE and SSR are the same for linear regression of one variable. Wait, am I making a mistake here? Huh? I don't think it is. They're not the same for this? Okay. So, SSE? All right, sure. Wait, so what's SSR then?
It's like y minus y bar. There's y minus y bar.
Okay. All right. Sure. Sorry. I'm labeling this wrong. Y minus y bar? But isn't
It's the RSS.
Huh? Yeah. Okay. RSS. All right. Okay. Residuals. Yeah. RSS. Okay. SSE. All right. Sorry. Thank you. Okay. So here, this is we've got this. Is this okay? The way I've defined this, And then, okay, so I went ahead and I went to Wolfram Alpha, and I said, can you simplify this for me, please? So I typed this in, 2 plus minus a and b plus 6 minus a 2b, so on and so forth. And then I said, solve it, and here it is in expanded form. This is a tiny bit easier. It's 4a squared plus 20ab, wrong button. So this is 4a squared plus 20ab minus 40a plus 30b squared. Wait, minus 40a plus 30b squared minus 116b plus 120. Okay, so this is now my function of a and b that I want to minimize here. Okay, so we've got this, and so now let's minimize this. Let me see if I can copy this. I don't have to rewrite this. Oops. Okay, so maybe we'll just start with some initial guesses. And so maybe, you look at your, we've got something like this. Maybe you say, we're going to say y hat is equal to 2x, right? So in this case, our initial guess will be a is equal to a0 will be 0, intercept of 0, and b0 will be a slope of 2, or something like that. Okay. So what we're going to do is we're going to write f of a and b, but we're going to set b equal to 2. So this becomes just a function of a, and if I plug in b equal to 2 everywhere, then we're going to have 4a squared plus 40a, right, minus 40a plus 30 times 4, which is plus 120, minus 116 times 2, what's that, 232 plus 120. So this becomes 4a squared minus 232. Is that right? I don't know. Okay. Let's ask Wolfram Alpha to do our homework for us. And so I'm going to say this, but we're going to set b equal to 2. Oh, I must have done something wrong. Wait, 4a squared plus 2. What? Oh, there's 2 positive 120s. Okay. Okay. Plus 8. Okay. 4a squared plus 8. Okay. Good. So I can't do math. All right. So then we just say, okay, where is this thing minimized? 4a squared plus 2. 4a squared, I'm sorry, plus 8. This is going to be minimized where a is equal to 0, right? Okay, so this is, okay, the minimum is at a equals 0, so that doesn't help us much, all right? But that's fine, okay? So this is minimized at a equals 0. All right, great. So then, once we have that, then we will take our function, a and b, and we'll plug in a equal to 0. And so this becomes 0 plus 0 minus 0 plus 30b squared minus 116b plus 120. 30b squared minus 116b plus 120. And then we'll ask Wolfram alpha to minimize that. So for any of these things, we could use like golden section search to minimize the function, or we could use Newton-Raphson method, or whatever we want to do, okay? We just have to minimize this function with respect to b, okay? Okay, and if I plug this in, I got 30b squared minus 116b plus 120. Okay, so I got 30b squared minus 116b plus 120. Okay, and so this is minimized at 29/15, okay? All right, so now I have a new value of b. We plug that back into our original function, and then we get a function of a, minimize it with respect to a, get a new value of a, plug that into the function, get a function of b, minimize there, go back and forth, and you just iterate back and forth, and eventually it will converge to the minimum, okay? And with least squares regression, there's only one minimum there. You don't have to worry about getting trapped at a local min or max or something like that. With least regression, that's what we have. And if we were to minimize the entire thing for least squares regression, we find that happens at a equal to 1 and b equal to 8/5, which is exactly what you would get if you plugged in your normal linear model least squares regression stuff for your slope and coefficient. I mean slope and intercept. Okay. All right. Are there any questions regarding kind of the iterative steps here? Yes?
Wait, so when you keep going back and forth, do you stop whenever like a is equal to what it was before?
Yeah, so yeah, how do we, when to stop, all right? So we have, some options. One is you can do, we'll say if the function of a, we'll say a(n) and b(n) minus kind of your previous values of a and b. Okay, if this is less than some tolerance. Okay, so that's one option for choosing when to stop. We can also do like if the Euclidean distance between a and b, your previous iteration, a b at time n minus 1, and a and b at time n, if that Euclidean distance is less than tolerance, or so this would be Euclidean distance, or you can also just do this is Manhattan distance, or this is your L1 norm versus your L2 norm. And so these are all kind of options. You probably wouldn't just look at one of the variables at a time. You'd have a look at both a and b together. But you can do kind of the Manhattan or the Euclidean distance, you know, your L1 or L2 norms. Yes?
Is this method guaranteed to converge for any initial guess?
Is it guaranteed? Let me think. So coordinate descent, no, it's not guaranteed. So what we have, okay, so when it comes to optimization, we have what's known as like convex loss functions, which would be least squares, sum of squares, residuals is known as a convex thing, meaning it has kind of this nice bowl shape. So we can find, like when we find the minimum, it's going to be the global minimum or something like that. But you don't always have, sometimes you'll have a function where it's like wobbly and whatnot, okay? And coordinate descent should get you to a local min or a local max, but knowing if the local min or max is the same as the global min or max, that's a very, very challenging problem that we don't have good answers for. So you know, a lot of the methods have been developed using kind of squared loss functions, because the squared function, you know, has like this nice quadratic, nice shaped parabolas and stuff like that, paraboloids or hyperparabolas. But yeah, not everything works that way. So yeah, no guarantees. Okay. For least squares regression, yes, it'll work. Okay. So you do have to code some of this up in your homework. All right, that's the last problem in the homework, and it should work out okay. But if you have any questions, you know, I'm happy to try to answer them. So or if we're good, we can end class here too. Okay, well then we'll end, and have a great weekend, and we'll see you guys next week. See you then. Okay.